Hey guys, welcome back to another chemistry lesson. Today we're going to start our conversation about types of bonds, chemical formulas, and compounds. So first we need to talk about chemical bonds and the types of compounds that we encounter in chemistry. Compounds are composed of atoms that are held together by chemical bonds. So it's not just a mixture of things, they are glued together. And chemical bonds result from the attraction between charged particles that compose atoms. And we're specifically talking about the electrons and the protons. And so our chemical bonds are broadly classified into these three types of bonds. We have ionic bonds, covalent bonds, and metallic bonds. So first, ionic bonds occur between metals and nonmetals and involve the transfer of electrons from the metal atom to the nonmetal atom. The metal atom then becomes a cation with a positive charge, and the nonmetal becomes an anion with a negative charge. So if we go from two neutral things to one positive and one negative. Now that we have these opposite charges, opposites attract and create this electrostatic force between them, which is the ionic bond. In a solid phase, the ionic compound is composed of this, what we call a crystal lattice structure, which is a regular three-dimensional organizational strategy, I guess, of alternating cations and anions. So here we have our sodium, which we've got as purple. We've got our chlorine, which we have as green. And here you see we have this alternating green and purple of the sodium chloride. And what that actually looks like differs depending on what the substance is. So sodium chloride is a 1-to-1 ratio, but there are other compounds like magnesium chloride that are not a 1-to-1 ratio. So this 3D structure looks a little bit different depending on what it is we're talking about, but you still have this alternating three-dimensional organization. Covalent bonds occur between two or more nonmetals, and instead of a give and take of electrons, what we get is a sharing of electrons between the atoms, and so therefore we get a molecule. So covalently bonded compounds are called molecular compounds, and this piece I feel like is pretty common sense, but I'm going to go ahead and say it. The most stable, the lowest potential energy, therefore this is what happens, that's what that means, is that the shared electron exists in that space in between the nuclei. It's not like out here in space or like over to one side. It exists here in the middle. So we have an atom, another atom, and then the shared electron exists where my face is, in that space in between. So let's talk about how we represent compounds, because we have to be able to look at them on a macro scale. We can't look at individual compounds. So a compound's chemical formula tells us what elements are in the compound and how many atoms or ions we have of each. So water is H2O, telling us we have 2 hydrogens and 1 oxygen. Sodium chloride is NaCl, telling us we have 1 sodium and 1 chlorine. Carbon dioxide is CO2, 1 carbon, 2 oxygens. Carbon tetrachloride is CCl4, 1 carbon, 4 chlorines. So that is a chemical formula. You need to get familiar with that. We're going to be using it a whole lot during this course. There are several different types of chemical formulas that we work with in chemistry, however. We've got empirical formulas, molecular formulas, and structural formulas. Empirical formulas are formulas that give the relative number of atoms of each element in a compound. It's not the exact number, but it's like if I had 100 guys and 50 girls, there are twice as many guys as there are girls, so 2 guys for every girl. 2 guys for every girl is the empirical formula of that situation that I just explained. The molecular formula gives the actual number of atoms of each element in a compound. So, for example, here we have H2O2. This tells us I have 2 hydrogens and 2 oxygens. That's the molecular compound. the molecular formula, excuse me. The empirical formula is, this is a 1-to-1 ratio, so 1H to 1O. B2H6 is the molecular formula, but there are 3 times as many hydrogens as there are borons, so BH3 is the empirical formula. It is possible to have a compound where the empirical formula and the molecular formula are the same thing. So CCl4, 1 carbon to every 4 chlorines. I can't reduce that number anymore, that ratio any further. I can't, like, if I have 1/4, I can't reduce that fraction any further. Same thing here. I can't reduce the ratio any further than 1 to 4. So 1 to 4, CCl4 is also the empirical formula. And then finally, we have our structural formula, which gives us a little bit more information. It's not just how many of the things that we have, it also shows us the order that they occur in. So we can look at it like this, which shows us that it's a hydrogen bonded to an oxygen, bonded to an oxygen, bonded to a hydrogen. Or we can even give a little bit of an angle to sort of hint at the 3-dimensional structure that exists in that compound. And the type of formula that we use totally depends on how much we know about the compound and how much we're trying to communicate about it. So if I don't know very much about the compound, maybe it's the empirical formula that I'm going to have. Or if I know the molecular formula but I don't know how the atoms are arranged, there we go. So again, structural formula tells us the most information, empirical communicates the least, so it's all dependent on what we know or what we're trying to communicate. We can also use molecular models, which use these really pretty 3-dimensional circles, but it's the more accurate way to completely tell us about the compound. The most common one that you probably have seen is a ball and stick model, which is exactly what it sounds like. You have these balls that represent the atoms and then sticks that represent the bond. And so in a ball and stick model, they're going to be, in a 3-dimensional arrangement so that we can see the 3D shape of the molecule. Typically, these balls are going to be color-coded to specific elements. It is kind of, sometimes if you have a physical model set, sometimes it's different depending on the model set, but typically we have this set color coding. And then we also have a space filling model, which is, instead of being able to see the sticks in the ball and stick model, what we have is more of a filled out atom. This kind of represents the nucleus, and this represents those shared electrons. So instead of showing that, we show the entire atom, and there is overlap. So you can see I don't have the full circle visible because we have this overlap where we have shared electrons. So this is the closest thing to what we would actually see if we could see a molecule on molecular scale. So those are the 4 different types of representations. So here we can see we've got benzene, which is C6H6. The empirical formula of that is CH. And here's our structural formula. You can see here 2 lines that represents a double bond, and ball and stick, space filling. Acetylene, also CH, but this is only C2H2, so we have a triple bond between our carbons that looks like this. Glucose is a much bigger molecule, C6H12O6, so C, twice as many hydrogens, and then O. So this is how we represent a compound, and which one we pick, totally dependent on what we're trying to do with that information.